In this lecture, I am going to discuss about symmetrical component analysis, or you can say Fortescue theorem. Basically, symmetrical component analysis is a technique through which you can analyze unbalanced and unsymmetrical three-phase power system on per-phase basis. In previous lecture, I have discussed about the balanced three-phase system. If the system is balanced three-phase system, then phase voltage of that system will be of equal magnitude. Magnitude of each phase voltage will be same. And the phase difference between the two phase voltage will be of 120 degree. And when you will represent the phase voltage through a vector diagram or phasor diagram, then what you will get? In the vector diagram, you will get three vector or three phasor, which is separated from each other by an angle of 120 degree. And length of the vector will also be same, because length represents the magnitude of the vector. So that type of system is called balanced three-phase system. And this is the phasor diagram of balanced three-phase system. You must note here, the length of each vector will be same, because length represents the magnitude of the vector, magnitude of the phase voltage. So if phase voltage of one phase is V angle 0, and which is a reference phase, then in clockwise direction, if you will take this angle in clockwise direction, then the phase voltage of this phase will be of minus 120 degree. Minus sign is due to clockwise direction from the reference phase. And this phasor represent voltage V angle plus 120, because from the reference, this phasor is in anti-clockwise direction at an angle of 120 degrees. So in anti-clockwise direction, you will have to take plus sign. So this is the phasor diagram of balanced three-phase system. So balanced three-phase system, in balanced three-phase system, phase voltage will be equal. Each phase voltage will be equal, and angle between two phase voltage will be of 120 degree. And when you will represent a three-phase system voltage with the vector diagram, then you will get three set of vector, and that vector will be separated from each other by an angle of 120 degree, and length of the each vector will be same. Now what is unbalanced system, which I have discussed in the previous lecture? You must go through that video where it is discussed, where discussion about balance and unbalanced system is presented. And the knowledge of balance and unbalanced system is very important to understand symmetrical component analysis. Now, consider the set of these three vector, and I am asking you whether this is balanced or unbalanced. You can easily say, sir, these phasors make an unbalanced system, because in this case you can see the angle between the phasor is not 120 degree. That is why this is unbalanced phasor. Or also you can see here the length of the vector. Length of the vector, which is shown in red color and white color and blue color, is not same. And the length represents the magnitude of the phase voltage. So you can say that the phase voltage differs from each other in this case. So that is why this is unbalanced system. Or you can say unbalanced phasor. Now what is symmetrical component analysis? According to symmetrical component analysis, three unsymmetrical and unbalanced phasor of three-phase system. This is unsymmetrical and unbalanced phasor of three-phase system can be resolved in three component. One component, three component, in which two component will make a balanced system and one component will be zero sequence component. According to symmetrical component analysis, the sets of these three unbalanced phasor can be resolved in three component, out of which two component will make a balanced system and one component will be zero sequence. And one balanced phasor is called positive sequence component. Other balanced system will be negative sequence component, and third component will be of zero sequence component. And what is the meaning of positive sequence, negative sequence component? A positive sequence component means the phase sequence of this unbalanced phasor, or the phasor uh, which is represented in positive sequence. The phase sequence of this phasor will be same as the original phasor. You can see here the phase sequence of the original phasor is RYB. I have discussed about the phase sequence in the previous lecture, so you must go through that video. And the phase sequence of this phasor will also is also RYB. Basically, phase sequence is the order in which phase voltages will attain their maximum. So you can see here the original phasor, which is unbalanced, has phase sequence RYB, and this phasor has phase sequence also RYB. So the phase sequence of this balanced phasor and this unbalanced phasor are same. So that is why this is called positive sequence. Now you can see the second balanced phasor. This is balanced phasor. Here phase sequence is R, B, Y. Here phase sequence is RBY. It is not same as the original phasor, but in opposition to the original unbalanced phasor. So that is why this is called negative phase sequence component. You must remember, for three-phase system, only two phase sequence is possible if you will take R as reference. One is RYB and another one is RBY. So you can see here the original phasor, which is unbalanced, has phase sequence RYB, and this phasor has also sequence RYB. So that is why this is called positive sequence. And this balanced phasor has phase sequence RBY, which is in opposite to the original phasor. That is why this is called negative phase sequence component. And this one is zero sequence component, in which all of the three phasor will be parallel to each other, and the magnitude of these three voltage will be same. VA naught will be equal to VB naught will be equal to VC naught. So in conclusion, you can say the symmetrical component analysis actually divide the unbalanced phasor in three components. One component is called positive sequence, and other component is called negative sequence component, and third sequence component is called zero sequence component. And but you must remember the positive and negative phase sequence components will make a balanced system. It means if you will add these three voltages in vector form, your result will be 0. Or you can say balanced system means the length of these three vector will be same, and the angle between the vector will be 120 degree. Here also the length of these three vector will be same, and the angle between the vector will be 120 degree. So you must remember, if three-phase system is unbalanced, then according to symmetrical component, 3 minus 1, 2. 2 will be balanced sequence component and 1 will be zero sequence component. If n phase system become unbalanced, then according to Fortescue theorem, according to symmetrical component analysis, if the system is of n phase and which is unbalanced, then you can resolve it into n minus 1 balanced phasor plus 1 zero sequence phasor. This theorem is called Fortescue theorem or symmetrical component analysis. So what is positive sequence component? A set of three phasor equal in magnitude, displaced from each other by 120 degree in phase, and have same phase sequence as the original phasor. You must remember. And what is negative phase sequence component? A set of three phasors equal in magnitude displaced from each other by 120 degree in phase and phase sequence opposite to the original phasor. And what is zero sequence component? Three phasor equal in magnitude with zero phase displacement between the phasor. So this is the meaning of positive, negative and zero sequence component. Once again, I am repeating the concept. According to Fortescue theorem, if this is unbalanced phasor, this is unbalanced phasor, VA, VB and VC. And according to Fortescue theorem, you can resolve these three unbalanced phasor in a set of two balanced phasor. In a set of two balanced phasor. This is balanced phasor. This is balanced phasor. And one zero sequence component. One zero sequence component. This is the Fortescue theorem or symmetrical component analysis. And you must remember, one balanced set will be of same phase sequence as the original phasor. Original phasor phase sequence is ABC. So this phasor phase sequence will also be ABC. And this balanced set is called positive sequence. This is positive sequence. And the other balanced set phase sequence will be opposite to the original phasor. The phase sequence of original phasor is ABC, but phase sequence of this phasor will be ACB. This is called negative sequence. And other last phasor will be parallel to each other. And this phasor is called zero sequence component. So this is called Fortescue theorem. And one point is very important here. These two sets are balanced set. Balanced set means if you will add these three voltage, you will get zero result. Your answer will be zero. If you will add these three voltage, you will get zero result. And the length of these three vector will also be same. Length of these three vector will also be same. And you must remember, length of the vector will represent the magnitude of voltage. So in this case, magnitude of VA1, magnitude of VB1 and magnitude of VC1 will be same. Similarly, in this case, magnitude of VA2, magnitude of VC2 and magnitude of VB2 will be same. So this is the meaning of balanced system. If there is a n-phase system and which is unbalanced, then according to Fortescue theorem, it can be resolved in n-1 balanced phasor. Balanced phasor plus one zero sequence phasor. This theorem is called Fortescue theorem. For three-phase system, n will be 3. So two balanced phasor and one zero sequence phasor. So this is called Fortescue theorem or symmetrical component analysis. And according to this theorem, if you want to write this unbalanced phasor VA in terms of symmetrical component, then this VA will be equal to VA1 plus VA2 plus VA naught. VA naught plus VA1 plus VA2. One zero sequence component, one positive sequence component, and one negative sequence component. Similarly, if you want to write VB, unbalanced phasor in terms of balanced phasor or in terms of symmetrical component, then this VB will be equal to VB naught plus VB1 plus VB2. Similarly, if you want to write down this unbalanced phasor VC in terms of symmetrical component, then this VC will be VC1 plus VC2 plus VC naught. So the set of unbalanced phasor, this is the set of unbalanced phasor which is resolved in two balance phasor and two balance phasor, and one zero sequence component. This theorem is called Fortescue theorem. Now in previous lecture I have discussed about the alpha operator. You must remember alpha. You must go through that video in which I have discussed about alpha operator, because that operator is very important here. And just I am going to revise it once again so that you can understand this theorem clearly. What is alpha operator? Basically alpha, you must go through the previous video about the alpha operator. Basically alpha is one angle 120 degree. And I have discussed in the previous video that when any vector A is multiplied with angle this operator alpha, then what will happen? This vector will rotate by an angle 120 degree in anti-clockwise direction. But its magnitude will be same. So if this is A, then this will be A into alpha. When you will again multiply alpha to this phasor, this vector, then again this vector will be rotated by an angle of 120 degree. But its magnitude will be same. And you will get alpha square, A alpha square. So alpha operator basically rotates the vector in 120 degree, rotates a vector by 120 degree in anti-clockwise direction. So you must remember about this. And in addition to this, various property of alpha operator have also been incorporated in the previous video. So you should go through that video for the better understanding of symmetrical component analysis. And second thing you must remember, if this is a vector A, and I'm asking you, what will be the phasor representation of this vector if this angle is 120 degree and length of these two vectors is same? Then your answer will be, sir, A alpha. You have to multiply alpha with it so that it can be rotated by an angle of 120 degree. So you must remember, when you will multiply alpha in this vector, then what will happen? This vector will rotate by an angle 120 degree in anti-clockwise direction. Or you can say the vector which is at an angle 120 degree from this reference vector of same magnitude can be written as A into alpha. So you must remember this to understand symmetrical component analysis or component synthesis and analysis equation. So here you can see, this is required here. This alpha operator is required here. If you want to write all of phasor in terms of phase A, then how you can write it? This is very important. You can see here, suppose the task is to write all of the phasor VA, VB, VC in terms of phase A only. How you will write? So you want to write unbalanced phasor in terms of A only. So VA is already in terms of A. Now VB is this. Now you want to write VB in terms of sequence component of phase A. How you will write? First, you know VB naught will be equal to VA naught, no problem, because it is equal in magnitude and direction. So phasor VA naught can be written as VB naught, or VB naught can be written as VA naught can be written as VB naught, and VC naught can also be written as VA naught, because these three vectors have same length and direction is also same. So you can write these three are equal in vector form, so no issue. So VB naught can be written as VA naught. But how you will write VB1 in terms of VA1, in terms of phase sequence component of A1? So let us see here. This is VB1. This is VB1. And you want to write this VB1 in terms of VA1. What you will do? What will happen if you will multiply this vector by alpha? When you will multiply this vector by alpha, then this vector will rotate in anti-clockwise direction by an angle of 120 degree, and its length will not change. So this vector is alpha VA1. You will get alpha VA1. This is the property of alpha operator. And when you will again multiply alpha to this vector, then what will happen? This will again rotate by an angle of 120 degree in anti-clockwise direction. And this, you will get this yellow vector, which is VB1. Now it become equal to alpha square VA1. So this is the role of alpha operator. So in place of VB1, you can write alpha square VA1, because VB1 is 240 degree in anti-clockwise direction from the VA1, and the length of VA1 and VB1 is same. So just you have to multiply alpha square in this vector, you will get VB1. So VB1 can be written as alpha square VA1. Similarly, VB2. Now let us see here, VB2. And now you want to write this VB2 in terms of phase A component, VA2. How you can write it? If you will multiply alpha in this vector, then what will happen? This vector will rotate in anti-clockwise direction by an angle of 120 degree, and you will get this yellow color vector. So VB2 can be written as alpha into VA2. Similarly, VC2 can be written as alpha square, because when you will multiply alpha in this again, then this factor will rotate 120 degree again, and you will get alpha square V2. So in this way, VC2 can be written as alpha square VA2. So this VB2 can be equal to alpha VA2. Similarly, VC naught can be written as VA naught. And if you want to write VC1 in terms of VA1, then VC1 will be alpha VA1. And VC2 will be alpha square VA2. In this way, you can see here, the set of three unbalanced phasor can be written in terms of phase sequence component of phase A. Means if you have an idea of phase sequence component of phase A, if you know the value of only one phase sequence component of only one phase. For example, if you know the phase sequence of component of phase A, then with that knowledge, you can determine VA, VB, and VC. You can determine phase voltage of all the three phases. So this is the technique. And this technique is called symmetrical component analysis. What you are analyzing here? If you know the value of phase sequence component of only one phase, for example, if you know the phase sequence component value of phase A, then by this knowledge, you can determine unbalanced phasor VA, VB, and VC. And in this, alpha operator is playing vital role. So the knowledge of alpha operator is very important to know the value of unbalanced phasor only with the value of phase sequence component of phase A. So this technique is called symmetrical component analysis. And if you will write this equation in matrix form, you can write this equation in matrix form. So in matrix form, this equation will be this. So in general, you can write VABC is equal to A and V012. You must remember VABC matlab VAVBC in column. It is a column matrix, and A is transformation matrix. This is called transformation matrix. When you will write these three equations in vector form, in matrix form, you will get this type of equation. And here this matrix is transformation matrix A, and 0, 1, 2 means VA0, VA, no, VA1 and VA2. In this way, VA, VB, VC can be determined from the knowledge of VA0, VA1 and VA2. This technique is called symmetrical component analysis, and this equation is called synthesis equation. Means if sequence components are available for any phase, then you can determine unbalanced phase. Similarly, if you will take inverse of this metric, if you want to calculate VA0, VA1 and VA2, what you will do? You will take inverse of this matrix. If you want to calculate VA0, VA1 and VA2 and VA, VB, VC is given, then how you will calculate? Just you will have to take inverse of this matrix. And when you will take inverse of the matrix, you know the formula of calculating inverse of matrix, you will get this result. So if unbalanced phasor is known, then from the 3 unbalanced phasor you can determine the sequence component. And this equation is called component analysis. So this is the component synthesis, and this one is the synthesis equation, and this is component analysis. This is component synthesis and this is component analysis. So you must remember these two metrics, which will play very important role in the remaining part of the course. So you must remember it. If unbalanced phasor is given, if symmetrical component is known, and you have to determine unbalanced phasor, VA, VB, VC, then you must remember this matrix. This is called synthesis. It is very easy to remember it. 1, 1, 1, 1, 1. Alpha square, alpha, alpha, alpha square. And this matrix will be started from A0, A1, and A2. This is called component synthesis. And if symmetrical you want to calculate symmetrical component and unbalanced phasor is known, then how you will calculate? How you will calculate? This will be again 1, 1, 1, 1, 1. Now it is alpha, alpha square and alpha square, alpha. So it is very easy to remember. Now unbalanced phasor will be given. So these two equations, these two matrices are very important for the remaining part of the course. So you must remember how you will determine unbalanced phasor if sequence component is given, and how you will determine sequence component if unbalanced phasor is given. And these two are very important. You must remember here alpha. I have discussed about the alpha in the previous lecture. Alpha is one angle 120, and the second thing which I have discussed in the previous lecture is 1 plus alpha square will be equal to 0. Alpha q will be equal to 1. So you just go through that video. Alpha conjugate will be alpha square. Alpha square conjugate will be equal to alpha. So you must go through that video. Otherwise, it would be very hard to understand symmetrical component analysis. So this is all about symmetrical component analysis. And in next lecture, I will discuss the application of the symmetrical component analysis.